We have so far looked at a wide range of instructions in the MIPS instruction set. In this video, we are going to look at a set of instructions which are necessary to support a very important higher level language feature, that of function call or procedure call. But first, let's test your understanding of the instructions we have seen so far. What instruction would you use if you wanted to subtract a constant, let us say 8, from a register? What instruction would you use if you want to multiply a value of a register by 4? What instruction would you use if you want to divide the value of a register by 8 and get the quotient? Now, if you wanted to divide the value of a register by 8 and get the remainder, what instruction would you use? What instruction or sequence of instructions would you use if you want to compare a register with a constant for equality and branch conditionally based on the comparison? So here is a summary of all the instructions we have seen so far. With respect to arithmetic, we have seen add, addi, and sub. With respect to logical operations, we have seen and, or, nor. Shift operations, SLL, SRL for left shift and right shift respectively. For memory operations, we have seen load word and store word. And for branch operations, we have seen conditional and unconditional. And a summary of the registers we have encountered so far in MIPS. Number wise, they are 0 to 31. In assembly language, they are also referred to by logical names. We have seen $S0 to S7, T0 to T9, as well as the special register $0, which is actually the register number 0 as well. Let us start by looking at what is needed to support function calls. Here we have a function f which is resident in memory. This is memory, and let's say function f, this is the body of function f in memory, and then the same program calls f multiple times. It will call multiple times. After all, that's one of the purposes of having a function, so that the same section of code can be used from multiple points in the code. So there are actually two instances of non-sequential execution in a function call. One is the call itself, where control is transferred from here to the beginning of the function, and then at the end of the function we need to transfer control back to the instruction after the function call. So we need to support function call as well as function return. So here is a question for you to think about. Just for this example I have shown here, where a function without any arguments is called, is it possible to support the function call itself using just the instructions we have looked at so far? The answer is yes, potentially. Just the jump instruction is sufficient. Now what about for the return? Is the set of instructions we have seen so far enough to support function return? The answer is no. That is because the point of return can be different each time, and it is not known to the body of the function as to where it should return. The body of the function by definition does not know where to return because it could be called from anywhere else in the code. So a simple solution is to remember the return point. In order to remember the return address at the point of calling, MIPS has a specific instruction for this. It's called JAL, which stands for jump and link. So you do JAL and label in assembly language, where the label is the starting point of the function. Now this JAL instruction does two things. One is it assigns PC plus 4 to a register, a special register $RA, which is part of the MIPS 32 set of registers, and it also does the jump and link. This is the linking part of jump and link, and then the actual jump happens, which is transfer control to wherever the label says. That is set PC equal to wherever f label refers to. So why here is $RA set to PC plus 4? Yeah, PC plus 4 is the point of return from the function call. That is the instruction sequentially next to the JAL call itself. We are only half done in the support for function call and return. We have now a mechanism to remember the point of return. We actually have to use it to return. This also cannot be done just by using the instructions we know so far. There is a new instruction which we need to introduce here. This is part of the MIPS instruction set, that's called jump register, JR. So jump register takes one register as argument, It can be any of the 32 registers. However, the function call return, if it does $RA, you realize that the function call will return to the correct point. So these two instructions, JAL and JR, are enough to support this particular example of function call we have seen. Now what about arguments and return values? Functions can have arguments and they can have return values as well. By convention, a set of registers are used for this. $A0, $A1, $A2 and $A3 are used to pass arguments to functions, and two registers $V0 and $V1 are used to pass return values from the function. Note that these are by convention and these are not enforced by hardware. These registers are also among the 32 registers in MIPS. This JAL and JR are sufficient to support the simple case of main function calling a function f multiple times. But what about nested function calls? Suppose we have a case of main calling a function f, which in turn calls function g. Is it possible to support this using just JAL and JR? If not, what would break? When f calls g, the return point to main from f gets overwritten. Do you think you can solve this problem by having, say, two registers $RA1 and $RA2, which are used to support this kind of nested function calls? Well, it might help in the case of nested function calls of depth 2, but the fact of the matter is that we can have nested function calls of arbitrary depth. We can have arbitrary nesting of function calls. In fact, the nesting of function calls which happens during runtime, it is not possible to know it during compile time. It is not possible to know it statically. So the question then arises, when there is arbitrary nesting of function calls of arbitrary depth, where can we store the return address in each case? We need a data structure for this, and the right data structure for storing the return address in the case of arbitrary nesting of function calls is a stack data structure. So using the stack, we can store the return address $RA onto the stack before making a function call and restore one's own return address from the stack after making a function call. So let's take a specific example. So let's take this example where main calls function f, which in turn calls function g1 followed by function g2. So in writing the assembly code for f, we can do as follows. Save $RA, that is the return point to main from f onto the stack before calling g1, and then restore the return address from the stack after the return from g1. Similarly, do the same thing for the call to g2. This is one possibility. Another possibility is as follows. At the very beginning of the code for f, we save $RA onto stack, make whatever nested function calls we want, and then before returning from f to main, restore $RA from the stack. Do you think the second option will work? Which of the two options is more efficient? Yeah, the second option is indeed more efficient and it will indeed work. So we need a stack data structure for implementing function calls, nested function calls. So how are we going to implement the stack in the machine? Where is the stack going to be? In MIPS, we are going to use a portion of the memory itself as the stack. So this is your main memory. This is the top portion of main memory, and somewhere along here is the bottom portion. So what would be the word address of the topmost word? Remember, the word address has to be a multiple of 4. So we have 0xFFFF The stack in MIPS grows from the top of the memory towards the bottom. It grows in this way. So this is somewhat counterintuitive because it's the opposite of what you've been used to. You've been used to stack growing up, but in implementation, the stack actually grows down from the top portion of the memory towards the bottom. And MIPS has a special register called $SP, which stands for stack pointer. This is the top of the stack, top of the logical stack, which is actually the least address of the occupied portion of the stack. This $SP is part of the MIPS set of 32 registers. So why does the stack grow downward? That we will answer shortly. So a question for you is, given that $SP points to the current top of the stack, write the MIPS assembly code to push $RA onto the stack. So this is the solution. $SP currently has something in it. In order to push $RA onto the stack, we need to decrement the stack pointer by 4, and then we get to the next free memory location onto which we store $RA. That is the store word instruction. Now the next question is, can you write the assembly code to pop $RA from the stack? This is the solution. We have to load from the current top of the stack $SP onto $RA, and then we have to increment the stack pointer, which denotes that the stack is being popped. Now what if there are arguments and return values in nested calls? So in the same example as earlier, main calls a function f which has arguments as well as return values. F in turn calls g, which also has arguments and return values. In this case, $RA is not the only register which needs to be saved onto the stack and restored. The registers which are used for passing arguments and return values also need to be saved and restored if necessary. So in this case, f as the caller of g will determine if it has to save and restore these registers, the argument registers and the return value registers, if the caller f cares. That is, if f is calling g at a point within its code where after that point it is going to use, let us say, argument register $A1, then it better save $A1 onto the stack before calling g, and then restore the value from the stack after the return from g. If there is an argument register or return value register which f does not care about after the point of calling g within its code, then it does not have to save and restore that particular register. Now, higher level languages often support an arbitrary number of arguments and arbitrary size of arguments. What if the set of arguments a function takes cannot be accommodated within the 4 registers designated within the hardware? Likewise, what if the return value cannot be accommodated within the given registers? Well, the answer is you use the stack for these situations as well. So we have seen that this register $RA has to be saved, and also potentially the argument and return value registers. It turns out that some registers are saved by the caller and some registers are saved by the callee. Let me elaborate what I mean by this by taking this example again, our familiar example. So here we have main calling f, which in turn calls g. So when main calls f, main is the caller and f is the callee. F also acts as a caller for function g, and g is a callee from function f. Now for each register in a nested function call situation, each register may be saved by the caller and restored by the caller, or it could be saved by the callee and restored by the callee. $RA is an example of a callee saved register. What it means here is that g as a callee needs to save and restore $RA to the original value as given by f if g happened to use this particular $RA. In this example, let's say that g makes no function calls. So g knows that it is not going to use $RA. So in this example, g as a callee need not save and restore $RA. However, f as a callee needs to save and restore $RA because f is potentially modifying $RA by calling function g. On the other hand, registers $A0 to $A3 as well as the return value registers are caller saved. So in this case, f is a caller of g if f cares about whatever registers values after the return from g, then it has to make sure that these registers are saved onto the stack and restored from the stack after the call from g. To be more concrete, suppose f were like this. It uses $A2 as an argument from main, and let's say after some point it calls function g, and then after the return from g it again uses $A2. In this case, it cannot rely upon G saving and restoring $A2. So it has to save and restore $A2 before and after the call respectively. This saving and restoring obviously uses the stack. So in a caller saved situation, the responsibility of saving and restoring is upon the caller. In other words, the callee can use those registers freely without having the responsibility of saving and restoring. On the other hand, in callee saved registers, the caller can assume that whatever value that register had at the point of calling will be restored by the callee before returning from the callee. So to reiterate, each register has to be saved and restored either by the caller or the callee using the stack. In caller saved registers, the responsibility of saving and restoring falls upon the caller. In callee saved registers, the responsibility of saving and restoring falls upon the callee. There is also another name for caller saved registers. They are called unpreserved, and this is because the value of the register cannot be guaranteed to be preserved. So when F calls G, the value of $A2 can be modified by G. F cannot assume that the value of $A2 will be restored. So if it is using $A2 after the call to G, it better save and restore. On the other hand, callee saved registers are called preserved registers, and this is because the caller can assume that the callee will save and restore the original value and need not worry about saving and restoring itself. So apart from $A0 to A3 and the return value registers, $T0 to T9 are also unpreserved or caller saved registers. Now there is a meaning to the letter T here. We can interpret that as temporary. Temporary in the sense that the callee can use it as it pleases without having the responsibility of preserving the value. Registers other than $RA which are preserved or callee saved are these. Note that $SP itself is not stored and restored from the stack. That would be absurd. It just means that the callee has the responsibility of returning the stack pointer to the same value as it was when it was called. Note that caller saving versus callee saving, a register being caller saved versus callee saved, is purely a convention. This is a convention followed by compilers. This is in no way enforced by the machine or hardware. If a compiler wants to follow a different convention, it can very well do so. So we have so far seen several uses of the stack. Saving registers including $RA as well as the argument and return value registers if necessary, we use the stack. If there is more number of arguments than can be accommodated in 4 registers, we use stack. More return value than 2 registers, then also we use the stack. There is another situation also where we need to use the stack. Can you think of what that might be? Yeah, stack is also used for supporting local variables in function calls. There is no other obvious place where you can support local variables if you think about it. So for each instance of a function call, we have a portion of the stack being used for that particular function call. This portion of the stack is used for different purposes as we have seen so far. The arguments beyond 4 registers, saving registers including $RA as well as local variables. So this portion of the stack corresponding to a particular function call is known as the stack frame or the call activation record of that particular function call. Note that one instance of a call activation record is created for each call activation of a particular function. Now MIPS provides another register which can potentially be used by the compiler to make its job easier. This is known as $FP, which stands for the frame pointer. So recall the stack frame from the earlier discussion. So this is the stack frame for a particular function or call activation record. $SP points to the bottom of the frame. $FP, if used, will point to the top of the frame. So can you think of a reason why we may need this frame pointer and how it can make the job of the compiler easy? A hint is, look at this particular function where there is a local variable x. It is used at point L1 and it is also used at point L2 where another local variable I has been introduced. The answer is that the reference to x at point L2 and L1 will be the same with respect to $fp. However, it will be different if you access it with respect to $sp. And the reason is that the stack has grown from point L1 to L2 to accommodate this additional local variable I. Again, the use of frame pointer $fp is optional. It is left to the compiler. Such use of frame pointer is in no way enforced by the hardware. Some compilers may choose not to use fp in this fashion. $fp is also a preserved or callee saved register. So the stack grows from the top of memory downwards. We're going to see the reason why now. It has to do with the overall memory organization. So this is your memory, starting with 0 to FFFF, FFFC. At the bottom of memory, we have a portion of memory reserved for the operating system. Then comes the text or the code corresponding to the program which is running. Then comes the data portion. The data portion corresponds to all your global variables in the program. So here we encounter yet another register in the set of MIPS 32 registers, that is $GP, which stands for global pointer. So there is a portion of data which is statically allocated in memory, and there is a portion of data which is the heap, which is dynamically allocated. Now we know the reason why the stack grows from the top of memory. The reason is that the heap, which is the dynamic data, grows from the portion where the static data ends upwards this way. And this is the portion where typically execution starts. The start of text $PC is set to this to start the execution of the program. So here is an example exercise which will put a lot of what we have talked so far together. Let's try and translate this recursive C code for computing the factorial of an integer into MIPS assembly code. So go on, take some time and give it a try. Here is my solution. I will explain it to you in the order in which I wrote it. I didn't quite write it from the beginning to end like it appears here. Started with the body of the function. So here, this is the if then else. If the argument happens to be non-zero, so I go to the else condition, and this is the base case, which is easy. Note that the function has one argument, one return value. So the obvious choice is to use A0 for the argument and register V0 for the return value. So I have to set V0 to 1 in the base case. That's this statement. The else case is the recursive call. So I first make the recursive call here by preparing the argument, and this is the recursive call. That's it, jal fact. Now when I return from the recursive call, I realize that I need my original argument n. Now the recursive call could have clobbered the original value of A0 which was there when I made the recursive call. So A0 is a caller saved register, so I as a caller have to restore it from the stack. So let me do load word. Here I actually don't know at this point when I'm writing the code the offset from $sp. So when I wrote it originally, I left this empty. It has to be restored somewhere from the stack, then multiply that with the return value from the recursive call, which is in $v0, and put the result also in $v0. So this is my return value. Now I'm ready to exit. So I realize that in the body I have to save, apart from $RA, $A0. So two things to save. So I now write the head of the function, which is essentially stack manipulation. I have to store $RA in the stack followed by $A0, and that's these three lines of code. And now I'm ready to fill in this 0 here because I have stored it at the top of the stack, and then before exiting I have to restore $RA, and I also have to restore $SP. Note that I don't have to restore $A0 here because as a callee I don't have the responsibility of handling $A0. So before returning I restore $RA, $SP and return. That's it. Before we end this video, I would like to mention a few details which we have missed along the way. The first is the notion of pseudo instructions. Now there are situations where the assembler would like to support some instructions which are not really there in the machine's instruction set. An example is this pseudo instruction called load immediate, which loads an immediate value onto a register. There is no real MIPS instruction called load immediate, but there are a couple of ways of implementing this using other instructions. Can you think of what you can use? Yeah, LI can be implemented either by using add-I under the covers or other instructions such as OR-I. Another example of a pseudo instruction is BEZ and BNZ, which stand for branch if equals 0 and branch if not equals 0. These are actually converted to BEQ and BNE, with one of the arguments being the $0 register. Now these pseudo instructions are provided by the assembler as programmatic sugar. These are converted internally by the assembler to other machine implemented MIPS instructions. Now there are some pseudo instructions which do not quite translate into machine instructions directly. Let's take this example, BEQ $S0 with the immediate value comparison to some label. Now this is a pseudo instruction because in the real machine instruction set, BEQ takes two register arguments. It doesn't take one register argument and one immediate argument. So how can we convert this into known MIPS instructions? You actually have to use another register. So this is what it gets translated into. You set a register here $AT to value 10 and then use that in a regular MIPS BEQ instruction. This AT stands for assembler temporary. So this is a register which is by convention left to be used by the assembler for such purposes. Note that this is a convention and the hardware does not enforce this kind of use of the assembler temporary register. Another example of the use of assembler temporary register is to support jumps which cannot be supported directly by the machine instruction jump with an immediate operand because it's too far away. So here what you do is use the assembler temporary. The assembler loads the assembler temporary register with an appropriate value and then uses the JR instruction internally to jump to that particular value. Another bit of detail which I have not covered so far is dealing with bytes and half words. We have MIPS instructions load byte, load half word, similarly store byte and store half word for dealing with bytes. So these deal with units of data which are smaller than one word. Now for load, we have corresponding unsigned versions as well. Load byte unsigned, load half word and signed. Now can you think of why we need separate signed and unsigned versions? Similarly, do you think we need instructions store byte unsigned, store half word unsigned? Why or why not? Here is a summary of what we have discussed so far. We are more or less done with the discussion of MIPS instruction set design. We have looked at MIPS instruction encoding, how regularity and simplicity plays a role here. We have looked at the set of instructions required for function call support and various conventions in terms of call activation record, callee saved registers, caller saved registers, and so on.